So let's take a look at tangent planes and linear approximations. So let's say we have a surface that has some equation z equals a multivariable function f of x comma y, and we're trying to find a plane that is tangent to the surface at a given point P, which has the coordinates x0, y0, and z0. So using this information, we can find the equation of the tangent plane, and the formula is going to be z minus z0 equals f sub x, so the partial derivative of the function with respect to x evaluated at x0 comma y0 times x minus x0 plus f sub y, so the partial derivative of the function with respect to y evaluated at x0 comma y0 times y minus y0. So that's going to be the formula. So for these problems, we have to find an equation of the tangent plane to the given surface at the specified point. So the given surface's equation is z equals 4x squared minus y squared plus 2y, and the specified point is negative 1, 2, 4. So the negative 1, 2, 4 is going to be the x0, y0, and z0. And so once again, the formula is up top here. So we already know what z0 is. Let's go ahead and find what f sub x is evaluated at x0 comma y0. So f sub x, or the partial derivative of the function with respect to x, is going to be, well, in this case we're going to take the derivative but treat x as the variable and everything else as a constant. So derivative of 4x squared is 8x, derivative of negative y squared is 0, and the derivative of 2y is also 0. So we get 8x, and now let's evaluate it at x0 comma y0. So in this case, negative 1, 2. So in this case, there is no y variable, so we don't have to substitute in 2. We just have to substitute negative 1 in for x. So negative 1 times 8 is negative 8. So now let's go ahead and find f sub y evaluated at x0, y0. So f sub y, we're still going to take the derivative, but this time treat y as the variable and everything else as a constant. So derivative of 4x squared is 0, derivative of negative y squared is negative 2y, and the derivative of 2y is positive 2. So we get negative 2y plus 2, and then if we evaluate it at x0, y0, we'll get, well, we don't have to plug in negative 1 because there's no x variable, but we do have to plug in 2 for y, so negative 2 times 2 is negative 4, plus 2 is negative 2. So that is going to be f sub y evaluated at x0, y0. So now if we write our formula here, once again it's going to be z minus z0, this time z0 is going to be 4, so z minus 4 equals, now f sub x evaluated at x0, y0 we got as negative 8, so negative 8 times x minus x0. x0 is negative 1, so if we subtract negative 1, we're going to add 1. And then plus f sub y evaluated at x0, y0, we find that to be negative 2. So we can add negative 2 or just say minus 2 times y minus y0. In this case, y0 is 2. So y minus 2. So if we go ahead and simplify this, we'll get z minus 4 equals, now I can distribute, so negative 8x minus 8 minus 2y plus 4. Now negative 8 plus 4 is negative 4, so we get z minus 4 equals negative 8x minus 2y minus 4. If I go ahead and add the 4 to the other side, they'll cancel. So the equation of the plane is z equals negative 8x minus 2y. So for number 2, we have z equals the square root of 4 minus x squared minus 2y squared, and the specified point is 1, negative 1, 1. So that is obviously going to be the x0, y0, and z0. And so once again, let's go ahead and first find f sub x, or the partial derivative of the function with respect to x, evaluated at x0, y0. So in this case, x0 is obviously 1, and y0 is negative 1. So the partial derivative of the function with respect to x is going to be, well, first I'm going to go ahead and change this function just a little bit so that instead of saying the square root, I write it as to the 1/2 power. So 4 minus x squared minus 2y squared to the 1/2 power, because I'm going to have to use the chain rule. So when I derive with respect to x, we're going to take the derivative of the outside function, so 1/2 times, now we're going to leave the inside function as it is, subtract the power by 1, so 1/2 minus 1 is negative 1/2, and then we can multiply by the derivative of the inside function. Now the derivative of the inside function Since we're deriving with respect to x, everything else is treated as a constant except for x. So derivative of 4 is 0, derivative of negative x squared is negative 2x, and the derivative of negative 2y squared is also 0. So notice that 2's will cancel. So up top on the numerator we'll get negative x over 4 minus x squared minus 2y squared if I move the exponent down to the positive 1/2 power. So now when we evaluate at x equals 1 and y equals negative 1, we'll get negative 1 over 4 minus 1 squared, so 1, minus 2y squared, so minus 2, to the 1/2 power. So 4 minus 1 is 3, 3 minus 2 is 1, 1 to the 1/2 is 1, so negative 1 over 1 will give us negative 1. So now let's find f sub y, the partial derivative of the function with respect to y, also at x0, y0. So once again, we're going to take the derivative of the outside function. So this is the same process, 4 minus x squared minus 2y squared to the negative 1/2 power. And then now we take the derivative, or multiply by the derivative of the inside function. Since we're deriving with respect to y, everything else but y is going to be treated as a constant. So derivative of 4 is 0, derivative of negative x squared is also 0, but the derivative of negative 2y squared is going to be negative 4y. So 4 over 2 is going to be 2, so we'll get negative 2y up top over, and then we have 4 minus x squared minus 2y squared to the positive 1/2 if I move that negative exponent to the denominator. And so we can go ahead and evaluate at x equals 1, y equals negative 1. And so when I do that, up top we'll get negative 2 times negative 1, so that'll give us 2, over 4 minus 1 squared, so that's 1, and then minus the same thing, so minus 2 to the 1/2. So on the bottom, as the before, we got 1, and then up top we'll get 2, so 2 over 1 will give us 2. So now we can go ahead and plug everything into the formula. So once again, the formula is z minus z0. Z0 is 1, so z minus 1 equals f sub x evaluated at x0, y0, which we got to be negative 1. So negative 1 times x minus x0. X0 is 1. Plus f sub y at x0, y0, which we found to be 2, times y minus y0. The y0 is negative 1, so we have plus 1. And then we go ahead and simplify. So z minus 1 equals negative x plus 1 plus 2y plus 2. So now z equals, now 1 plus 2 is 3, and if I go ahead and add over the 1, we'll get 4. So negative x plus 2y plus 4. Now this is an acceptable answer, but if you want to put all the constants on one side and the variables on another side, we go ahead and add the x and subtract the 2y. So we'll get positive x minus 2y plus z equals 4 as the tangent plane equation. So now for number 3, we have z equals y times cosine of x minus y at the specified point of 2, 2, 2. So that once again is going to be the x0, y0, and z0. So let's go ahead and find f sub x, or the partial derivative of f with respect to x, evaluated at x0, y0, so at 2, 2. So once again, that is going to be equal to, now x is the variable that we derive, and everything else is going to be constant. So since y is a constant, the derivative of cosine is negative sine, so we have y times negative sine of the inside function, x minus y, times the derivative of that inside function. Since we're deriving x and y is a constant, the derivative of x is 1, and derivative of negative y is 0, so we can just leave it as it is and multiply by 1. So then we'll get negative y times sine of x minus y. So now if we evaluate it at 2, 2, we have negative 2 times sine of 2 minus 2, which is 0. Sine of 0 is 0, so then we'll get the answer of 0. So now let's find f sub y, or the partial derivative of the function with respect to y, evaluated at x0, y0. So now, since y is the variable that we derive, it's in two separate functions, so we have to use the product rule. So using the product rule here, we have two separate functions. So we're going to take the derivative of the first. So the derivative of y is 1. So 1 times the second unchanged, which is just cosine of x minus y, plus the derivative of the second one. The derivative of cosine of x minus y is going to be negative sine times x minus y times the derivative of the inside function. So the derivative of x minus y, if we're deriving with respect to y, derivative of x is 0 and derivative of negative y is negative 1. And then times the second function unchanged, so times y. So then we'll get cosine of x minus y. Well, negatives will cancel, so we'll get plus y times sine of x minus y. So if you evaluate it at x naught, y naught, so 2, 2, we'll get cosine of 2 minus 2, so cosine of 0, plus 2 times sine of 0. Sine of 0 is 0, so that will cancel. Cosine of 0 is 1, so we're left with 1. So now let's go ahead and use the formula. So once again, z minus z naught is going to be 2. So z minus 2 equals f sub x evaluated at x naught, y naught, which we found to be 0, times x minus x naught, so x minus 2. Notice that doesn't even matter since we're multiplying by 0, so that will cancel. And then plus f sub y evaluated at x naught, y naught, which we found to be 1, times y minus y naught, which is 2. So now if we simplify, we get z minus 2 equals y minus 2. So if I add the 2's, we'll cancel, and so the final answer is z equals y. So now the next set of questions is going to be about linearization. So let's say we're trying to find the linearization of a function f of x comma y at a certain point. And let's say that point has the x coordinate a and the y coordinate b. So the formula is going to be L of x comma y is going to be equal to f of a comma b plus the partial derivative of f with respect to x evaluated at a comma b times x minus the x coordinate a plus f sub y, the partial derivative with respect to y of a comma b times y minus the y coordinate b. So for these next set of problems, let's find the linearization of the function at the point. So the given function is f of x comma y is x times the square root of y, and we have to find the linearization at the point 1, 4. So since 1 is the x coordinate, that's going to be the a, and then 4 will be the b value. So once again, we're going to take f of a comma b, so f of 1 comma 4, we're just going to go ahead and evaluate the multivariable function at 1, 4. So that is going to be equal to 1 times the square root of 4. Square root of 4 is 2, so 1 times, or 2 times 1 gives us 2. So now let's find f sub x, or the partial derivative of the function with respect to x, at a comma b. So f sub x at 1 comma 4 is going to be equal to, now x is going to be what we derive, so y is going to be the constant. So the derivative of square root of y times x, or x times the square root of y, is simply just the square root of y. And so if we evaluate that at 1, 4, there is no x variable, so we don't have to worry about the 1, but we have to plug in 4 for y, so we get the square root of 4, or 2. So now let's find f sub y at a comma b. So f sub y, partial derivative with respect to y, evaluated at 1, 4, is going to be, well, x is going to be treated as a constant, square root of y is the variable, so we're just going to have x times the derivative of square root of y is 1 over 2 square root of y. So we basically get x over 2 times the square root of y. Now if we evaluate that at 1, 4, we're going to get 1 over 2 times the square root of 4, which is 2, so 2 times 2 is 4. So plugging in all the numbers to the formula, L of x comma y, the linearization of the multivariable function, is going to be f of a comma b, which we have found to be 2, plus the partial derivative of f with respect to x evaluated at a comma b, which we found to be 2 as well, times x minus a, so x minus 1, which is right there, plus f sub y evaluated at a comma b, which we found to be 1/4, times y minus b, and the b is 4, or the y coordinate. So when we simplify, we'll get 2 plus 2x minus 2 plus 1/4 y minus 1. So 2 minus 2 will cancel. So we'll get the linearization of x comma y equals 2x plus 1/4 y minus 1. So for number 2, we have f of x comma y equals inverse tangent of x plus 2y at the point 1, 0. So that is going to be our a and b. So let's first go ahead and find f of a comma b. So f of 1, 0. Once again, we're just going to evaluate what we have here as a multivariable function. So that is going to be inverse tangent or arctangent of 1 plus 0, so 1. Now arctangent of 1 is obviously pi over 4. So now let's find f sub x, or the partial derivative of the function with respect to x, evaluated at 1, 0. So partial derivative of x, now remember, x is going to be the variable, y is the constant. So the derivative of inverse tangent of some function u is going to be u prime over 1 plus u squared. So if x plus 2y is the inside function, let's go ahead and find the derivative of the inside function. So if we're deriving with respect to x is going to be the variable, y is the constant, so the derivative of x is 1, derivative of 2y is 0, so we get 1 on the numerator, over, now 1 plus u squared, so the entire inside function squared, so x plus 2y squared. Now if we go ahead and evaluate that at 1, 0, we'll get 1 over 1 plus 0 squared, so 1 squared is 1, so that will give us 1/2. So now let's find f sub y, evaluated at 1, 0. So same process here, we're still going to take the derivative of arctangent and use a similar formula, but now we're deriving with respect to y, so y is the variable, x is the constant, so u prime here in this case, derivative of x is 0, derivative of 2y is 2, so 2 over 1 plus u squared, so that inside function x plus 2y, the entire thing squared. So if we evaluate, go ahead and evaluate at 1, 0, we'll get 2 over 1 plus 1 squared, which is 1, so 2 over 2, which will give us 1. So now let's go ahead and use the formula. So L of x comma y is going to equal f of a comma b, which we found to be pi over 4, plus f sub x evaluated at ab, which we found to be 1/2, times x minus a. The a value is obviously 1, plus f sub y evaluated at 1, 0, which we found to be 1, times y minus the b value, which is 0. So if I go ahead and distribute, we'll get pi over 4 plus 1/2 x minus 1/2 plus y minus 0, plus y. And then if I go ahead and rearrange the terms, we get L of x comma y equals x over 2 plus y plus pi over 4 minus 1/2. And that's the final answer. So now the next set of questions is going to be about differentials. So let's say we have some equation z equals a multivariable function f of x comma y. So then the differential formula is going to be dz is going to be equal to the partial derivative of f, partial derivative of the function with respect to x, times dx, plus the partial derivative of f with respect to y, times dy. But now let's say you have a function with 3 inputs. So this time w equals f of x comma y comma z. The process is still the same and the formula is very similar here. So dw this time is going to be equal to the partial derivative of f with respect to x dx, plus the partial derivative of f with respect to y dy, and then plus, with the addition of z, the partial derivative of f with respect to z dz. So let's go ahead and find the differential of the function. So number 1, we have z equals x cubed times ln of y squared. So once again, dz, in this case we have a 2 variable input function, so both x and y. So dz is going to equal the partial derivative of f with respect to x dx, plus the partial derivative of f with respect to y dy. So the partial derivative of f with respect to x, let's go ahead and find that first. So we can also write it as f sub x This time x is going to be the variable, y is the constant. So derivative of x cubed is 3x squared multiplied by the constant ln of y squared. And so now the partial derivative of f with respect to y, or f sub y, this time y is going to be the variable, x is going to be a constant. So x cubed is just a constant multiplied by the derivative of ln of y squared. So now remember, the derivative of ln of u is going to be equal to u prime over u. So we're going to take the derivative of the inside function, which is 2y, over the inside function itself, y squared. So if we simplify 2y and y squared, we'll get 2 over y. So f sub y is going to be 2x cubed over y. So if we go ahead and write the differential now, dz is going to be equal to the partial derivative of f with respect to x, which we've found to be 3x squared ln of y squared. Remember, we have to multiply it by dx because it's a differential, plus f sub y, which we found to be 2x cubed over y, multiplied by dy. So for number 2, we have u equals e to the t times sine of theta. Notice there are no x and y, but there is t and theta. So we basically treat them the same exact way. So du is going to equal the partial derivative of u with respect to the first variable, let's just say that's t, times dt, plus the partial derivative of u with respect to now theta, times d theta. So let's go ahead and find the partial derivative of u with respect to t. So t is going to be the variable we derive, theta is going to be a constant, so the partial derivative is going to be e to the t sine of theta. Since the derivative of e to the t is still e to the t, and sine of theta is a constant. And so the partial derivative of u with respect to theta this time, now theta is going to be the the variable we derive, t is going to be a constant, so we get e to the t times the derivative of sine of theta, which is cosine of theta. So that is going to be the derivative of u with respect to theta. So du is going to be equal to derivative of u with respect to theta, the partial derivative, which is e to the t sine of theta, times dt, plus the partial derivative of u with respect to theta, which we found to be e to the t cosine theta, times d theta. And that's the final answer. So now for number 3, we have w equals natural log of the square root of x squared plus y squared plus z squared. Notice we have 3 input variables now, x, y, and z. So once again, dw, or the differential derivative of w, is going to equal the partial derivative of w with respect to x times dx, plus the partial derivative of w with respect to y dy, plus the partial derivative of w with respect to now z times dz. So let's go ahead and first find the partial derivative of w with respect to x. So once again, the derivative of the natural log of some function u is going to be u prime over u. So we're going to take the derivative of this entire inside function. Notice that it includes the square root as well. So the derivative of square root of x squared plus y squared plus z squared, I can also rewrite it as x squared plus y squared plus z squared to the 1/2 power. So the natural log of this entire thing. And so if I take the derivative of this, I'm going to have to use the chain rule. So we bring the power down, keep the inside function the same, subtract the power by 1, so 1/2 minus 1 is negative 1/2, and then multiply by the derivative of the inside function. Since we're deriving with respect to x, x is going to be the variable, everything else is a constant. Derivative of x squared is 2x, derivative of y squared is 0, and z squared is also 0. So notice that 2's will cancel, so we're left with x over x squared plus y squared plus z squared to the 1/2 power. So now let's find the partial derivative of w with respect to y. So once again, it's the same process. We're going to take the derivative of the inside function. So once again, it's still going to be 1/2 times x squared plus y squared plus z squared to the negative 1/2. And then this time, we're going to multiply by 2y. Because since y is the variable, everything else is a constant. Derivative of y squared is 2y. Derivative of x squared is 0. Derivative of z squared is also 0. 2's will cancel. So we'll get y over x squared plus y squared plus z squared to the 1/2 power. And so now, in order to find partial derivative w with respect to z, notice it's going to be the exact same pattern, and so we can go ahead and skip ahead a little bit. Since this one has the same denominator, it's just the variable that changes on the numerator. So since we're deriving with respect to z, then we'll have z on the top over x squared plus y squared plus z squared to the 1/2 power. So if I go ahead and write the differential now, we get dw equals, now partial derivative w with respect to x, we found that to be x over x squared plus y squared plus z squared to the 1/2, now times dx, plus the partial derivative of w with respect to y, we found that to be y over the same denominator, times dy, and the same thing goes with the partial derivative of w with respect to z. And then we can multiply, go ahead and multiply by dz. So we get z over x squared plus y squared plus z squared to the 1/2 times dz. Now since these are all the same common denominator, I can actually add the numerators since the denominator is the same. So I'm going to go ahead and move the dx up top here. So rewrite it as x dx. I can rewrite it as y dy, and then rewrite it as z dz. So dw, if I add up all the fractions with the same common denominator, is going to be x dx plus y dy plus z dz, all over the same common denominator, x squared plus y squared plus z squared to the 1/2. So that is going to be the differential.